The mathematics of general relativity refers to various mathematical structures and techniques that are used in studying and formulating Albert Einstein's theory of general relativity. The main tools used in this geometrical theory of gravitation are tensor fields defined on a Lorentzian manifold representing spacetime. This article is a general description of the mathematics of general relativity. Note: general relativity articles using tensors will use the abstract index notation. Why tensors? The principle of general covariance states that the laws of physics should take the same mathematical form in all reference frames and was one of the central principles in the development of general relativity. The term general covariance was used in the early formulation of general relativity, but is now referred to by many as diffeomorphism covariance. Although diffeomorphism covariance is not the defining feature of general relativity, and controversies remain regarding its present status in GR. The invariance property of physical laws implied in the principle, coupled with the fact that the theory is essentially geometrical in character, suggested that general relativity be formulated using the language of tensors. This will be discussed further below. Spacetime as a manifold. Most modern approaches to mathematical general relativity began with the concept of a manifold. More precisely, the basic physical construct representing gravitation, a curved space-time, is modeled by a four-dimensional, smooth-connected, Lorentzian manifold. Other physical descriptors are represented by various tensors, discussed below. The rationale for choosing a manifold as the fundamental mathematical structure is to reflect desirable physical properties. For example, in the theory of manifolds, each point is contained in a coordinate chart, and this chart can be thought of as representing the local spacetime around the observer. The principle of local Lorentz covariance, which states that the laws of special relativity hold locally about each point of spacetime, lends further support to the choice of a manifold structure for representing spacetime as locally around a point on a general manifold. The region looks like or approximates very closely Minkowski space. The idea of coordinate charts is local observers who can perform measurements in their vicinity also makes good physical sense, as this is how one actually collects physical data, locally. For cosmological problems, a coordinate chart may be quite large. Local versus global structure. An important distinction in physics is the difference between local and global structures. Measurements in physics are performed in a relatively small region of space-time, and this is one reason for studying the local structure of space-time in general relativity, whereas determining the global space-time structure is important, especially in cosmological problems. An important problem in general relativity is to tell when two spacetimes are the same, at least locally. This problem has its roots in manifold theory, where determining if two Riemannian manifolds of the same dimension are locally isometric. This latter problem has been solved, and its adaptation for general relativity is called the Cartan-Carladi algorithm. Tensors in general relativity. One of the profound consequences of relativity theory was the abolition of privileged reference frames. The description of physical phenomena should not depend upon who does the measuring. One reference frame should be as good as any other. Special relativity demonstrated that no inertial reference frame was preferential to any other inertial reference frame, but preferred inertial reference frames over non-inertial reference frames. General relativity eliminated preference for inertial reference frames by showing that there is no preferred reference frame for describing nature. Any observer can make measurements, and the precise numerical quantities obtained only depend on the coordinate system used. This suggested a way of formulating relativity using invariant structures, those that are independent of the coordinate system used, yet still have an independent existence. The most suitable mathematical structure seemed to be a tensor. For example, when measuring the electric and magnetic fields produced by an accelerating charge, The values of the fields will depend on the coordinate system used, but the fields are regarded as having an independent existence. This independence represented by the electromagnetic tensor. Mathematically, tensors are generalized linear operators, multilinear maps. As such, the ideas of linear algebra are employed to study tensors. At each point of a manifold, the tangent and cotangent spaces to the manifold at that point may be constructed. Vectors are defined as elements of the tangent space and covectors are elements of the cotangent space. These two vector spaces may be used to construct type tensors, which are real-valued multilinear maps acting on the direct sum of copies of the cotangent space with copies of the tangent space. The set of all such multilinear maps forms a vector space, called the tensor product space of type it and denoted by. If the tangent space is n-dimensional, it can be shown that, in the general relativity literature, it is conventional to use the component syntax for tensors. A type tensor may be written as where as a basis for the ith tangent space and a basis for the jth cotangent space. As spacetime is assumed to be four-dimensional, each index on a tensor can be one of four values. Hence, the total number of elements a tensor possesses equals 4r, where r is the sum of the numbers of covariant and contravariant indices on the tensor. Symmetric and antisymmetric tensors and physical quantities are represented by tensors not all of whose components are independent. Important examples of such tensors include symmetric and antisymmetric tensors. Antisymmetric tensors are commonly used to represent rotations. Although a generic rank R tensor in 4 dimensions has 4 R components, constraints on the tensor such as symmetry or antisymmetry serve to reduce the number of distinct components. For example, a symmetric rank 2 tensor satisfies and possesses 10 independent components, whereas an antisymmetric rank 2 tensor satisfies and has 6 independent components. For ranks greater than 2, the symmetric or antisymmetric index pairs must be explicitly identified. Antisymmetric tensors of rank 2 play important roles in relativity theory. The set of all such tensors, often called bivectors, forms a vector space of dimension 6, sometimes called bivector space. The metric tensor. The metric tensor is a central object in general relativity that describes the local geometry of spacetime. Using the weak field approximation, the metric can also be thought of as representing the gravitational potential. The metric tensor is often just called the metric. The metric is a symmetric tensor and is an important mathematical tool, as well as being used to raise and lower tensor indices. It also generates the connections which are used to construct the geodesic equations of motion and the Riemann curvature tensor. A convenient means of expressing the metric tensor in combination with the incremental intervals of coordinate distance that it relates to is through the line element. This way of expressing the metric was used by the pioneers of differential geometry. While some relativists consider the notation to be somewhat old-fashioned, many readily switch between this and the alternative notation. The metric tensor is commonly written as a 4x4 matrix. This matrix is symmetric and thus has 10 independent components. Invariance. One of the central features of GR is the idea of invariance of physical laws. This invariance can be described in many ways, for example, in terms of local Lorentz covariance, the general principle of relativity, or diffeomorphism covariance. A more explicit description can be given using tensors. The crucial feature of tensors used in this approach is the fact that the operation of contracting a tensor of rank R over all R indices gives a number, an invariant, that is independent of the coordinate chart one uses to perform the contraction. Physically, this means that if the invariant is calculated by any two observers, they will get the same number, thus suggesting that the invariant has some independent significance. Some important invariants in relativity include the Ricci scalar, the Kretschmann scalar. Other examples of invariance in relativity include the electromagnetic invariance, and various other curvature invariants, some of the latter finding application in the study of gravitational entropy and the Weyl curvature hypothesis. Tensor classifications. The classification of tensors is a purely mathematical problem. In GR, however, certain tensors that have a physical interpretation can be classified with the different forms of the tensor usually corresponding to some physics. Examples of tensor classifications useful in general relativity include the Segre classification of the energy-momentum tensor and the Petrov classification of the Weyl tensor. There are various methods of classifying these tensors, some of which use tensor invariance. Tensor fields in general relativity. Tensor fields on a manifold are maps which attach a tensor to each point of the manifold. This notion can be made more precise by introducing the idea of a fiber bundle, which in the present context means to collect together all the tensors at all points of the manifold, thus bundling them all into one Grom object called the tensor bundle. A tensor field is then defined as a map from the manifold to the tensor bundle, each point being associated with a tensor at. The notion of a tensor field is of major importance in GR. For example, the geometry around a star is described by a metric tensor at each point. So at each point of the space-time the value of the metric should be given to solve for the paths of material particles. Another example is the values of the electric and magnetic fields and the metric at each point around a charged black hole to determine the motion of a charged particle in such a field. Vector fields are contravariant rank 1 tensor fields. Important vector fields in relativity include the 4 velocity, which is the coordinate distance traveled per unit of proper time, the 4 acceleration and the 4 current describing the charge and current densities. Other physically important tensor fields in relativity include the following: the stress-energy tensor, a symmetric rank 2 tensor; the electromagnetic field tensor, a rank 2 antisymmetric tensor. Although the word tensor refers to an object at a point, it is common practice to refer to tensor fields on a spacetime as just tensors. At each point of a spacetime on which a metric is defined, the metric can be reduced to the Minkowski form using Sylvester's law of inertia. Tensorial derivatives. Before the advent of general relativity, changes in physical processes were generally described by partial derivatives. For example, in describing changes in electromagnetic fields. Even in special relativity, the partial derivative is still sufficient to describe such changes. However, in general relativity, it is found that derivatives which are also tensors must be used. The derivatives have some common features, including that they are derivatives along integral curves of vector fields. The problem in defining derivatives on manifolds that are not flat is that there is no natural way to compare vectors at different points. An extra structure on a general manifold is required to define derivatives. Below are described 2 important derivatives that can be defined by imposing an additional structure on the manifold in each case. Affine connections. The curvature of a spacetime can be characterized by taking a vector at some point and parallel transporting it along a curve on the spacetime. An affine connection is a rule which describes how to legitimately move a vector along a curve on the manifold without changing its direction. By definition, an affine connection is a bilinear map, where is a space of all vector fields on the spacetime. This bilinear map can be described in terms of a set of connection coefficients specifying what happens to components of basis vectors under infinitesimal parallel transport. Despite their appearance, the connection coefficients are not the components of a tensor. Generally speaking, there are D3 independent connection coefficients at each point of spacetime. The connection is called symmetric or torsion-free, if a symmetric connection has at most 1/2 D2 unique coefficients. for any curve in 2 points, and on this curve, an affine connection gives rise to a map of vectors in the tangent space at A into vectors in the tangent space at B, and can be computed component-wise by solving the differential equation being the vector tangent to the curve at the point. An important affine connection in general relativity is the Levi-Civita connection, which is a symmetric connection obtained from parallel transporting a tangent vector along a curve whilst keeping the inner product of that vector constant along the curve. The resulting connection coefficients can be calculated directly from the metric. For this reason, this type of connection is often called a metric connection. The covariant derivative let be a point, a vector located at, and a vector field. The idea of differentiating it along the direction of in a physically meaningful way can be made sense of by choosing an affine connection and a parameterized smooth curve such that the formula for a covariant derivative of a long associated with connection turns out to give curve-independent results and can be used as a physical definition of a covariant derivative. It can be expressed using connection coefficients. The expression in brackets, called a covariant derivative of and denoted by, is more often used in calculations. A covariant derivative of x can thus be viewed as a differential operator acting on a vector field sending it to a type tensor, and can be generalized to act on type tensor fields sending them to type tensor fields. Notions of parallel transport can then be defined similarly as for the case of vector fields. By definition, a covariant derivative of a scalar field is equal to the regular derivative of the field. In the literature, there are three common methods of denoting covariant differentiation. Many standard properties of regular partial derivatives also apply to covariant derivatives. In general relativity, one usually refers to the covariant derivative, which is the one associated with Levi-Civita affine connection. By definition, Levi-Civita connection preserves the metric under parallel transport. Therefore, the covariant derivative gives 0 when acting on a metric tensor. It means that we can take the metric tensor in and out of the derivative and use it to raise and lower indices. The Lie derivative, another important tensorial derivative, is the Lie derivative. Unlike the covariant derivative, the Lie derivative is independent of the metric. Although in general relativity one usually uses an expression that seemingly depends on the metric through the affine connection, whereas the covariant derivative required an affine connection to allow comparison between vectors at different points. The Lie derivative uses a congruence from a vector field to achieve the same purpose. The idea of Lie dragging a function along a congruence leads to a definition of the Lie derivative, where the dragged function is compared with the value of the original function at a given point. The Lie derivative can be defined for type tensor fields and in this respect can be viewed as a map that sends a type to a type tensor. The Lie derivative is usually denoted by where is the vector field along whose congruence the Lie derivative is taken. The Lie derivative of any tensor along a vector field can be expressed through the covariant derivatives of that tensor and vector field. The Lie derivative of a scalar is just the directional derivative. Higher rank objects pick up additional terms when the Lie derivative is taken. For example, the Lie derivative of a type tensor is more generally, in fact, in the above expression. One can replace the covariant derivative with any torsion-free connection or locally, with the coordinate-dependent derivative, showing that the Lie derivative is independent of the metric. The covariant derivative is convenient, however, because it commutes with raising and lowering indices. One of the main uses of the Lie derivative in general relativity is in the study of space-time symmetries where tensors or other geometrical objects are preserved. In particular, Killing symmetry occurs very often in the study of spacetimes. Using the formula above, we can write down the condition that must be satisfied for a vector field to generate a Killing symmetry.